Okay, quiz 19.3, we're going to apply everything we've learned about the Nernst equation here. The half cells that are used in this electrochemical cell will reduce lead 2+ to lead and oxidize aluminum to aluminum 3+. It'll be operated at 25 degrees Celsius, which is 298 Kelvin. And this we're reducing lead 2+ to lead. That's going to require 2 electrons, and we're going to be oxidizing aluminum solid to aluminum 3+, and that is going to release 3 electrons. Now, we don't need to balance this chemical equation completely, but we should recognize that the 2 electrons and the 3 electrons are only going to match one another if we multiply this by 3, and that will give a total of 6 electrons. Multiply this by 2, and that will give 6 electrons. So 6 is the number that we need for applying the Nernst equation. Sorry, there's one more little bit that we should get here. Q is going to equal, if we combine these two together, then we would have 2 aluminum 3+ as product. So we'll go Al3+, and that will be squared. And then the lead is going to be times 3, and that's on the reactant side. So we're going to have Pb2+, and we will cube that. And then the reality is, if you balanced this, it could have some H3O+, if it is balanced in acid, or it could have some OH- if it is balanced in base. But looking at this, there are no oxides or anything like that. This is one reaction that actually will not have any acid or base in its balanced chemical equation. In fact, we've pretty much balanced it here. Why don't I just go ahead and write out the complete equation? So that would be 3 Pb2+ aqueous plus 2 Al solid. That will be in equilibrium with 3 Pb solid plus 2 Al3+ aqueous. Okay, if I had given you a redox reaction that would have unbalanced oxygens or hydrogens at this point, then the water and H+ and OH- might come into play and give you a more complicated reaction quotient. I intentionally chose a simple one for you. All right, so we haven't even gotten to question 1, but knowing that this is about the Nernst equation, I wanted to kind of gather everything that we needed before we proceed with the actual questions. Okay, so question 1, find E0 for the cell. So E0 is going to equal the reduction potential for the cathode. Cathode is where reduction occurs. That's your lead 2+ being reduced to lead. If you look at the table of standard reduction potentials, you'll find that that is a negative 0.13 volts. And then we'll subtract the standard reduction potential for the anode, which is the aluminum side. In the reduction potential table, you'd be looking for aluminum 3+ being reduced to aluminum solid. And that is a negative 1.66 volts. And so this is going to equal a total of 1.53 volts. That's the standard cell potential. Okay. Question 2. So based on the E0 cell, can we find the standard Gibbs energy? So delta G0 is going to equal negative NF E0. So that's a negative 6 times 96,485 coulombs per mole times 1.53 volts. And that is equal to a negative 885,730 joules, or in other words, negative 886 kilojoules per mole. That should have been per mole as well. Kilojoules per mole. Okay, question 3. Uh-oh, I hear crying again. Let me pause this. Hopefully that worked last time. I haven't actually checked. Okay, that time it was a 3-year-old, but nothing a little Baby Shark video couldn't fix. So based on this E0 cell, we want to find the equilibrium constant. So E0 is equal to RT over NF times the natural log of K. So this becomes 1.53 volts is equal to N of 6, F of 96,485 coulombs per mole over 8.314. Oh, hold up. I've got those backward. RT over NF, I'm sorry. R is 8.314 joules per mole Kelvin. T is 298 Kelvin over N is 6, and F would be 96,000, what is it, 485? 485 coulombs per mole times the natural log of K. Do I have enough room? I do. So the natural log of K in this case would equal 357.3. We'd raise E to 357.3 and we end up with K equal to 1.49 times 10 to the 155th power, which is now the biggest number we've seen yet in this class. Larger than a Google, which is 1 to the 100th. That is the equilibrium constant. Okay, find E for this cell if we're given different actual concentrations. So I'm going to go ahead and erase the last two problems so that we have room. So we're going to use the equation E is equal to E0 minus RT over NF times the natural log of Q. So our cell potential is going to equal the standard cell potential, 1.53 volts, minus 8.314 joules per mole Kelvin times the temperature of 298 volts over 6 is our number of electrons transferred times 96,485 coulombs per mole times the natural log of Q. Now in this case that's going to be 0.125, that's the concentration of aluminum, and that will be squared over the concentration of the lead, which is 0.250 cubed. And I actually did not intend this to happen, but when I worked out the answer, that reaction quotient actually ended up being a 1. It was coincidental, and I'll change it for next year because it kind of makes this question a little trivial, but I thought it was interesting. You can get a reaction quotient of 1, of course, if you have concentrations that aren't equal to 1 molar each. In fact, they don't even need to be equal to each other. Because this is squared and this is cubed, you get the interesting situation where you've got actually a higher concentration of lead than aluminum, but the quotient ends up being 1. Of course, the natural log of 1 is 0, and so we end up with E equal to 1.53 volts. Okay. Here we go. Will the voltage increase or decrease if this cell is placed in a refrigerator? So this is actually a bit of a tricky question. You can't quite answer it, but you can talk about factors that might affect it. So let's first of all set aside the fact that E naught is temperature dependent. And let's just look at this second half, the RT over NF ln of Q. So the effect that this side would have, if Q is greater than 1, then that means that this is a positive value, and higher temperatures would have the effect of decreasing the voltage. Lower temperatures then, putting in the refrigerator, would increase the voltage if Q is greater than 1. If Q is less than 1, then this is a negative value. It's multiplied by a negative number, and so that will make it a positive value. And increasing higher temperatures would tend to raise the voltage away from the standard potential. And so putting it in the refrigerator would decrease the voltage. But that's ignoring the fact that your standard cell potential is itself dependent on temperature. And so if we remember the relationship between E and K, and we think about the Chatelier's principle and its relationship to K, let's just, I'm running out of space. Let me erase a bunch here. It is no longer relevant. This is a bit of a challenge question. I don't think you need to know any of this, but maybe it's just interesting to you. Okay, so our relationship between E and K is that E naught is equal to RT over NF times the natural log of K. And so generally speaking, if you have a product favored reaction, then ln of K is going to be positive, and increasing the temperature will lead to a more positive E naught. If you have a reactant favored K, then ln of K is negative, and increasing the temperature will lead to a more negative E naught. But there's even like a third level. This is like temperature dependence inception, and that is that K itself is temperature dependent, and that'll depend on whether the reaction is exothermic or endothermic. And so if it's exothermic, then we would put heat as a product, and increasing the temperature would drive the reaction more toward reactants, and that would tend to reduce the value of E naught, either make it smaller positive number or a larger negative number. It will drive it left on the number line for exothermic. So for endothermic, this is exo. For an endothermic reaction, the heat would be on the left, and so increasing the temperature would drive it more toward products, and that would, increasing the temperature then would make for a larger K and a higher E naught, or in other words, a battery with higher voltages at higher temperatures. Okay, now, so disentangling these three effects, the effective temperature here, the effective temperature there, and the effective temperature there, could be quite complex, but just as a bit of an anecdote, my mom used to have a box that we would stick in the refrigerator that was full of our batteries when we wanted to put batteries in our Walkman or whatever. We would find fresh batteries in the refrigerator, and that was because she claimed, at least, that it made them last longer. They would not discharge on their own as quickly if they were in the refrigerator. And so for the nickel cadmium type batteries that used to be the norm, it was true that reducing the temperature would first of all reduce any reaction rates, but really it's not a kinetic consideration. Turns out that reducing the temperature would actually reduce the voltage, and so that would reduce any leakage currents that might happen inside the battery. So my mom was right, I suppose, to keep our batteries in the refrigerator. The key that I posted doesn't really go into all of the complexity of this question. I just kind of analyzed only the temperature dependence of temperature here. But it's actually a complex question, so I wouldn't worry too much about it. I thought it was kind of interesting that I wanted to bring in the anecdote about my mom and the batteries in the fridge. I wonder if I'm the only one